Okay, hi, my name is Alena, and I'm going to be taking you through question 3 of Spring 25 midterm. So in this question, we have some vulnerable C code that we're going to answer some questions on, given some assumptions, such as stack canaries are enabled. We have some shellcode that we might want to run later, and then we also have the address of buff. So the first question, 3.1, asks to fill in the blanks in the stack diagram, assuming the program is paused on line 3. So in the middle of the foo execution. So I think there's a lot of ways you can approach this problem. For me, I think the simplest is to remember that above every SFP for a function call, we're gonna want an RIP. So most likely for blank number 2, we're gonna have the RIP of foo. And then the second thing we want to remember is that we have stack canaries enabled and these go under the SFP. So for blank 1, we can have the canary of main. And then for blank number 3, we'll have the canary of foo. So this layout corresponds to answer B. Great. So 3.2, what type of vulnerability is present in this code? So judging by this vulnerable getS function call, I would infer that the vulnerability here is going to be buffer overflow, where we can now overwrite our buff past the 16 character limit. Format string vulnerability, yes, we see a printf here, but besides that, it doesn't seem too helpful to execute the whole vulnerability for signed and unsigned. There is no signed integers here that are being casted to unsigned integers. And then off by 1, we don't see any loops or bounds that have an off by 1 error. So it does seem like our inference of buffer overflow seems right here. All right, so in the next 3 subparts, provide an exploit that executes shellcode. 3.3 says to give an input to fread on line 4. So if we look back at our code, we kind of see 2 entry points for inputs. We have this fread on line 4 and this getS on line 6. So we can kind of infer that for the layout of our attack, we want to use this first entry point to leak our canary, and then on line 6 to actually use our canary, now that we have it, to finish our exploit. And so knowing this, now we know that our goal for 3.3 is to essentially give an input that will leak the stack canary. So how can we do this? We can notice that our canary is right above buff. Combined with the fact that we have this printf call here that actually prints buff, we can make sure that there's no null terminators between buff and canary, so that when we printf buff, it will continue printing past buff and hopefully print our canary since it's right after buff. So how we can do this? Well, the easiest way is actually just to fill buff with garbage, answer C. And this is because printf doesn't add a null terminator or anything, so we just want to make sure there's no null terminators in buff itself. Question A and B could also work, but because the question says that if the input can be any non-zero value, to use garbage. So these answer choices are a bit too specific to what we actually need for this to work. Answer D is incorrect because we're putting a null terminator in buff, so that when we call printf on buff, it will actually stop printing when it sees the null terminator, and it will actually never print out the canary. Okay, so for 3.4, let output be the value printed by the program from the printf on line 5. Which slice of output gives the value of the stack canary, assuming you have the correct input to the previous subpart. And so, for example, the 0 through 4 gives the first 4 bytes of output. So we know that printf starts at buff. So we know, because buff is 16 bytes long, that the first, actually, 0, okay, yeah. The first 16 bytes of output is going to be buff. So this will be 0 through 16, because the first number is inclusive, but the second number is exclusive. And so canary will just be the next 4 bytes since it's right above. So this will be 16 through 20 of output. And this corresponds to answer E. All right. So 3.5, let canary be the correct slice of output from the previous part. Give an input to gets on line 6. Okay, so now we have the freedom to rewrite what buff is. Okay, so I copied the question or the code and the stack diagram over here so that maybe we can have some more scratch work for this question. So our goal for buffer overflow is we're going to try to rewrite the RIP to our shell code address. But all we're provided is the shell code. So we'll also have to think about where we want to place that. And then we're also given the address of buff. All right, so basically how we can do this is execute a classic buffer overflow solution where we don't really care what's in buff. So we can do garbage here. And then the canary we got from our previous part, canary. We don't really care what the SFP of foo becomes. So we can also put garbage here. And then, yeah, we want to overwrite the RIP. So we haven't discussed that yet. And then maybe we can put our shellcode above the RIP. And so how do we calculate now this address, which is also the address of right here in our stack? Well, actually now we can use the address of buff. And we can just simply calculate that this address, it should be 28 bytes, I believe. 16 plus 4 plus 4 plus 4 is 28 above buff. So if you add 28 bytes to this address, you should get 0x f f f f f f b c. And so this will be our address of our shellcode. And because that's the address of our shellcode, the RIP should be overwritten to, let me make sure I write this correctly. Because we're in Little Endian, we should flip all of this. So this to BC, and then FF, FF, FF. Cool. So it looks like, and also buff will be written from bottom to top, right? So this looks like this corresponds to option A in our answer choices. Cool. And then I think I did want to point out that it's okay that we overwrote this canary, since by the time, because the canaries are usually checked after the corresponding function returns. So because our shellcode will execute before main returns, this will not crash because it hasn't checked the canary of main yet. Okay. 3.6 says, Which memory safety defenses, when enabled alongside stack canaries, would cause the correct exploit without modifications to fail? Consider each choice independently. So, actually, both of these defenses will work. For A, because we're changing the pointer of the rip of foo, then this change will be detected, and so our exploit as is will not work. And then B, non-executable pages also works because, as we said, we placed our shellcode right on top of the rip, which is on the stack. So if we make it so that nothing on the stack can get executed, then our exploit as is will fail. Okay. For the rest of this question, ASLR and stack canaries are both enabled, and the next two subparts provide an exploit that executes shellcode. So given in 3.7 says given input to fread on line 4. So this part kind of doesn't change because the purpose of this fread is to leak the stack canary, and we still have stack canaries enabled. We kind of still want to do the same thing. So the answer to this question is still gonna be to just feed in garbage into buff. But 3.8 is where things get a little different. So let output be the output from the printf call on line 5. You may slice this value, and you also may perform arithmetic on this value and assume it will be converted to/from the correct types automatically. Also let canary be the correct slice of output from 3.4. Fill in each blank with an integer to provide an input to the getS call on line 6. Okay, and then it's just saying these will get concatenated together. Okay, so let's look at how we should change our previous answer. So what ASLR does means that every time we run the program, addresses on the stack are going to change. And so looking at our exploit, the only thing that ASLR kind of defeats is this hard-coded address that we put straight into our exploit. However, we can use relative addresses to subvert this ASLR. How we can do that is recall that the SFP of foo will actually be pointing to the top of the previous stack, right? So it will be pointing to the SFP of main, like the address of, that address. And notice that we put our shellcode right under it. So why this matters is similar to how we can leak the canary. We can also leak the value of SFP of foo. And so we can leak this address right here. So leak this address. And then because the address we actually want is right under it, then we can take this address and subtract it by 4 in order to get the address we want. And so as we said, buff is going to be output of 0 to 16, and then the canary is going to be output of 16 to 20. Then this address that we want is going to be output of 20 to 24. And that's all that we need to change, is going to be to get rid of this hard-coded address and now put, this subtracted by 4 into our exploit. So to now fill it all in, as we said, our first part of our exploit will just be garbage to fill up buff, then our canary, and then we'll have garbage for the SFP of foo, And then we have our relative address of our shellcode, which we said was going to be output of 20 to 24 minus 4. And then finally our shellcode. And this should work. Cool. So I think that was the end of question 3. So hopefully that made some sense.